Good evening, everyone. So I'm going to discuss these things. Question number 8.5 of the chapter Mechanical Properties of the Solid. So I welcome you all in a Sapience Education once again. So how to solve this? Let us read the question first of all. Two wires of the diameter 0.25 centimeter, one made up of steel and another made up of brass, are loaded as shown in a figure. So this is the figure. So this wire of the steel as well as wire of the brass has been used here, and there is a two types of load. Okay, the unload length is given as 1.5 meter, so it has 1.5 meter, and that of the brass is equal to 1 meter. Okay, compute the elongation of the steel and the brass. So we need to find the elongation of the brass as well as steel elongation. So when we talk about the steel, so first of all I will talk about the steel wire. Okay, if there is a steel wire, so let us do this. This is 1.5 meter. This is the load. So load is not only 4 kg, but it has been attached with the 6 kg. So total load is how much, or total force is how much? 4 plus 6 into 9.8. So this will be 96. This will be equal to 98 Newton. So we have got the force acting on this. As we know that stress that is equal to Young modulus of elasticity into strain. So here stress is equal to force by area, and this is equal to Young modulus of elasticity into change in length by original length. Now we need to compute change in a length, that is delta L. So delta L is equal to FL by A into Young modulus of elasticity. Now we need to put here the values of the each and everything for the copper. So I want change in length for the steel wire. So for a steel wire, the force acting is how much? So force acting is 98 Newton into length of the steel wire is 1.5 divided by area of the steel wire. Area is equal to pi by 4 into diameter. So diameter of the steel wire they have given as diameter of two wire of a diameter is given as 0.25 centimeter. So this will be 0.25 centimeter. So convert it into meter whole square. So we have got the area into what is the Young modulus of the steel. So we know that Young modulus of steel Ys is equal to 2 into 10 to the power 11 Newton per meter square. So here we can use this 2 into 10 to the power 11. So finally if we calculate this, so we will have a 98 into 1.5 divided by pi into 4 into 0.25. So 0.25 whole square into 2 into 10 to the power 11 to 2 is 4, so 7. So when we calculate this, so we will get the value is equal to 1.49 into 10 to the power minus 4 meter. So this is the elongation of steel. This is our elongation of a steel. It is an elongation of steel. Okay, elongation of steel wire. I hope you have understood this. Now we need to think about the elongation for the brass. So when we talk about the elongation for the brass, so what we have to do? See here, elongation. So same formula, delta L for the brass is equal to force on the brass into length of the brass divided by area of the brass into Y Young modulus of the brass. So force on the brass, see if it is if you see here, if you see this brass, so what will happen, only brass, only 6 kg load is acting here, so we need to put here 6 into 9.8 into length of the brass is 1 meter. Okay, divided by area of the brass, so area will be same, so pi by 4 into 0.25 into 10 to the power minus 2 whole square into what is the Young modulus of brass, so this will be 10 to the power 11 only, 10 to the power 11. So when we will compute this, so we will get 1.2 into 10 to the power minus 4 meter. So this is elongation of the brass. Hence, elongation of a brass is equal to 1.2 into 10 to the power minus 4 meter. I hope you have got this. Now let us read this question 8.6. The edge of an aluminum cube is 10 centimeter long and one face of the cube is firmly fixed to a vertical wall. So let us make draw the diagram. Let us consider this is the cube. Okay, this is the cube, and the edge of this cube, that is this one has been firmly fixed in the wall. Okay, so this has been fixed firmly in the wall. Now they are telling that a mass of 100 kg is then attached to the opposite face of the cube. So this is the mass of 100 kg. So this is the mass of 100 kg means 980 Newton. 980 Newton load. 980 Newton load has been attached to the opposite force of the cube. The shear modulus they have given as shear modulus is 25 gigapascal. What is the vertical deflection? So if we simply draw the plane diagrams, so they want this. See here, this is the earlier situation, but when we apply a load, so what happened? Its shape gets changes. Its shape gets changes, right? So we want vertical deflection. So we want vertical deflection means this deflection we want. Let us suppose this deflection is x, and this length is suppose length they have given as L. This is theta. So we know that the important relation that it act as a right angle triangle. It act as a right angle triangle. So for right angle triangle, theta is equal to x by L. So which gives x is equal to L theta. Now the thing is that we need to find a theta. Okay. If we need to find the theta, so we know that famous relation that shear stress tau is proportional to shear strain, that is theta, shear strain that is theta, or tau is equal to g into theta. Now the value of g is given as 25 gigapascal. Mm, that is equal to 25 into 10 to the power 9, 10 to the power 9 pascal or Newton per meter square they have given. Now if we want to find the theta, so we have to find the tau. So tau is what? Stress, shear stress. Tau is our shear stress. Shear stress. See here, why it is shear stress? Because see here, force is acting parallelly to the surface area. So force, this is equal to force by area. So our force is 980 Newton divided by area. Area is how much? The area of the cross section, that is, since it is your cube having a side 10 centimeter long, so this is 10 into 10 into 10 to the power minus 4 meter square. So finally it will be 980 into 10 to the power square. So this is the shear stress. Now we have got the shear stress, we have got the value of G, so we can easily find out now theta. So theta is equal to tau divided by G. So tau is your 980 into 10 to the power 2 divided by G. G is our G is 25 into 10 to the power 9. So when we calculate these things, so what we are going to get the theta. Okay, so theta is approximately is equal to 3.9 into 10 to the power minus 6. Since it is your dimensionless, because theta is in radian, so it is your dimensionless, so no unit is required. Now we need to find x. So x is equal to what? L into theta. So L is how much? L is 10 centimeter means 0.1 meter into theta is 3.9 into 10 to the power minus 6. So when we multiply it, so we will get 3.9 into 10 to the power minus 7. So this is the x. So hence we have got, hence the vertical deflection of this face is equal to 3.9 into 10 to the power minus 7. So I hope you have understood this solution. Thank you. Hello. Now see here, question number 8.7. Four identical hollow cylinder column of a mild steel support a big structure of a mass 50,000 kg. The inner and outer radii of the column are 30 and 60 centimeter respectively. Assume that the load distribution to be uniform. Calculate the compressional strain of each column. Compressional strain means whenever, let us understood the situation or scenario, if there is a huge structure, so let us consider this is a structure and this structure has been supported by four of the columns. How many columns? Four columns. So let us put here one column here, another one column is there, another may be the column third one, and there may be the fourth one. Okay, so there is a four columns. Okay, now for each column the load is uniformly distributed, so each load at each column will be how much? Load at each column will be 50,000 into 9.8 divided by 4. So we will get this load at each column. Okay, this Newton, this amount of Newton we load at each column will be there. We need to find the compressional strain. So strain at each column, E we have to find. Okay, now as we know that stress is proportional to strain. Stress is proportional to strain, or stress is equal to Young modulus of elasticity into strain. Since either it is a tensile or compression, so you have to use Young modulus of elasticity only. So we need to find E, that is equal to sigma by Y. Now sigma is your force, that is load at each column divided by area into Young modulus of elasticity. So for what, since it is made up of steel, mild steel, so you have to use Young modulus of elasticity for the steel. Steel is how much? So steel is, it is equal to 2 into 10 to the power 11. So can we use here now the area? Since the area, let us consider this is the column, this is your column, and there is a area of the column. So the area, this amount of area is this, we need to calculate. Why? Because it is they have given inner and outer diameter, it means that it is hollow cylinder. So the area we should find first of all area. So area will be how much? Pi into r square. So r inner radii, outer radii minus inner radii, so this will be 30 square, or it is centimeter, so it will be 0.3 minus sorry, it will be outer radii will be here, outer radii is 0.6 centimeter, so whole square minus 0.3 whole square. So this is the area. So when we put the all values, so we will get the strain. So strain is equal to force. Force is how much? Force is we or load in each column is this. So this will be 50,000 into 9.8 divided by 4 into what is the area of the column. So area will be pi into 0.6 whole square minus 0.3 whole square into y value, gamma value or Young modulus of elasticity of the steel. So this will be 2 into 10 to the power 11. So finally we need to calculate this. So if we calculate this, so we are getting the values which is equal to 7.2 into 10 to the power minus 7. This is unitless quantity. Okay. Hence compressional strain for each column is equal to 7.2 into 10 to the power minus 7. So this is our correct answer. Okay. So I hope you have understood this question. Thank you. Let us see question number 8.8. So read this question. A piece of copper having a rectangular cross-sectional area of this is pulled in a tension with 44500 Newton force, producing only elastic deformation. Calculate the resulting strain. So we need an strain. So let us draw the situation or a scenario of this column or of this rectangular copper block. So let us consider this is a rectangular copper block. Okay. This is a rectangular copper block. And the cross-sectional area for this is how much? 15.2 mm into 19.1 mm. So they have given the area and is pulled in a tension. So they have been pulled in a tension. So tension with the or a force or load, we can say here 44500 Newton. Okay. So it has been pulled here, producing only elastic deformation. So calculate the resulting strain. So we know the formula stress is equal to Young modulus of elasticity into strain. So for getting strain, we need sigma by y. So stress is force, that is load by area into y. So finally, if you put the value, so we will get the result. So let us put the value. So strain is equal to force. Force is how much? 44500 divided by area. So area is basically area of the rectangle is length into width, that is equal to 15.2 into 19.1. Since it is in mm, so we need to convert it into meter. So this is 10 power minus 6 meter square. So if you want to convert it into meter, from mm square to meter square, so we have to multiply it by 10 power minus 6. So we have converted this. Now it is a term of y. So y for copper is how much? So we should remember these things, or sometimes they will provide you the data. So y for a copper is 42 into 10 to the power 9. So when we put here 42 into 10 to the power 9, so we will get some of the results. So when we put all the values, so we are going to get the result as 3.65 into 10 to the power minus 3. Hence the resulting strain, hence resulting strain is equal to 3.65 into 10 to the power minus 3. I hope you have understood this situation of the question. Okay. Now let us solve question number 8.9. Before that, we need to read the question. A steel cable with a radius of 1.5 centimeter supports a chair lift at a sky area. If the maximum stress is not to be exist, then 10 to the power 8 Newton per meter, what is the maximum load cable of the cable support? So let us, that sky rope, there is a chair. So let us consider this the chair, and it has been used for by the cable is used for supporting this chair. So this is a cable made up of steel. Okay, now the radius of the cable they have given. Now what is the maximum load the cable can support? So that is force they are asking. So maximum force is how much? So they have already given maximum stress is equal to 10 over 8 Newton per meter square. Now we need to know that how to find a maximum load. So we know that sigma is equal to force by area of the cross section of the cable. So if we have a sigma max, so sigma max is equal to force max into the area. So area they are not going to change. So from here, maximum force is equal to stress into maximum stress into area. So maximum stress is 10 to the power 8 into area of the cable, that is equal to pi into r square. So when we do this, pi into r square, that is equal to 1.5 into 10 to the power minus 2 whole square. So when we find this, so we will get a 7.068 to 10 to the power 4 Newton. So hence maximum, hence here, hence maximum load the cable can support is equal to 7.068 into 10 to the power 4 Newton. I hope you have understood this question. So this is very simple. I don't think it required more formulas and more complicated. So it is very simple question. I hope you have enjoyed this solution. Now let us solve question number 8.10. A rigid bar of a mass 15 kg is supported symmetrically by 3 wires, each of 2 meter long. Those at each ends are copper and middle one is of iron. Determine the ratio of their diameter if each is to have the same tension. Now see here. Let us draw the situation before solving it. Let us take the situation. So this is a rigid bar And this bar is weight is how much? Its weight is 15 kg into 15 into 10. So this is 150 Newton. Okay, and it has been supported. It has been supported by 3 ropes or 3 wire. So it is made up of copper. It is also made up of copper, but at the middle one, it has been it is made up of iron. Okay. Now, as per the situation, all wire has same tension. All wire has same tension, right? Now the thing is that all will have a same deflection. All will have same deflection. Why? Because when it will come down, so it has been told that determine the ratio of their diameter, 3 wire, those at each end of the middle one. So when it will move down, so each and every one will get deflection by delta x. Here also delta x, here also delta x. Okay. Now let us see here our formula for a stress strength. So stress is equal to Young modulus of elasticity into strain. So stress is your force by area, and this is equal to Young modulus of elasticity into delta L by L. Now if we think that about what delta L, so delta L is equal to FL by AY. Now since delta L, that is deflection, or delta L that we have considered here as delta X, is same for all. So same deflection is there, it means delta X or delta L is same. Delta L is same for all wire. So if delta L is same for all wire, so can we write here force F for copper, length of the copper divided by area for the copper into Young modulus of elasticity for copper is equal to F for iron. So if we talk about iron, so F force on iron into length of the iron divided by area of the iron into Young modulus of elasticity of the iron. Now let us see here what we need to cut here. Since force or tension, since tension is same, so tension means the force or the load. Load is equal to force. So force is same, so force will get cancelled out. Length of the each wire is also same, so length will get cancelled out. Now, what about area? So we want the ratio of the, determine the ratio of the diameter of each. So if we want diameter ratio of the diameter, so we can find like this: area of the copper divided by area of the iron is equal to Young modulus of elasticity for iron divided by Young modulus of elasticity for copper. Area for copper is equal to pi by 4 into diameter of the copper whole square divided by diameter of the iron whole square. Pi by 4 will be common, so this will get cancelled out. So why Young modulus of elasticity of iron by Young modulus of elasticity of the copper. Now if we see here D of the copper divided by D of the iron, we want to find the ratio. So this will be is equal to root under y the iron divided by y for the copper. Now if we want to put the value, so we know that the Young modulus of elasticity for the copper and iron is Young modulus of the elasticity for the copper and iron is how much? So Young modulus of elasticity for iron is 2 into 10 to the power sorry, iron, it is your iron for iron, it is different. For iron, yeah, iron for iron Young modulus of elasticity is 190 into 10 to the power 6 into 10 to the power 9 into 10 to the power 9 divided by Young modulus of elasticity for a copper is equal to 120 into 10 to the power 9. So when we do this calculation, so we will get the ratio is approximately is equal to 2.5 times diameter of copper divided by diameter of iron. It means that the diameter of the copper should be more thicker than the diameter of the iron. So from this we have got the conclusion that the diameter of the copper is your diameter of the copper is 1.25 times the diameter of the iron. Hence this is the ratio. So this ratio they are asking. I hope you have understood this and enjoyed this solution. Thank you for watching my videos. We'll meet in the next time. Thank you.